All right, I will now erase this and go to the second part. And this is exactly what we have used with Kevin to study the probability of this messenger RNA to reach the boundary without being destroyed, because we had these two, one was protecting, one was destroying. And so then we wanted to make sure that you could calculate this, and there is many possibility to escape for these guys. Suppose it can escape with 0 molecule bound. It can escape if the threshold to killed is, let's say, 5. If you can escape with 4. You can escape with 3, 2, 1 of these bad guys that are bound. So you can escape in many different stages. So this is why we need to look in this, I will show you the second Markov chains. We have to classify and to look what are the region of interest, what we want to calculate. Okay, so now let's go to part number 2. So let's work 5-10 minutes, and I think it's going to be enough for today. We'll continue next time, finishing this, and we will be able to start a polymer model next week, applied to double-strand DNA break and Ross polymer and looping. So for today now, I want to discuss time to threshold, or let's call it so Markov chains with killing. I'll explain in a second what I mean by this. This is really two-dimensional Markov chain with killing. All right, so suppose this is a picture we have in mind. You have the binding site. Time 0, let's suppose the particle enters, or they're already, you start time 0 and they are all there. And then there is a small hole. A small hole, if you remember, the time to escape through a small hole is Poissonian. So this small hole means a particle disappears. If it disappears, it's equivalent to say that the particle has been killed. I don't care where it has been killed, but it disappeared from the system. So now, we are interested, so let's suppose we call mu the Poissonian killing rate. Poissonian killing rate. So, what are we interested in here? We would like to understand, as a function of time, what is the probability that the number of bound molecules, this is number of bound, equals k, and the number of molecules in the system is m. So m is the total number of m molecules. Right, so this is the probability that ms, number of bound at time t, equals what? Equals k, and how many molecules we want to have? The number of molecules, which I call w, equals m. Condition that at time 0, ms is 0 and w equals m0. We introduce at time 0 all the molecules equals 0 and this. And the total number w at time t, this is the number of molecules that are free plus the number of molecules that are bound. This measures the total numbers, m of t and ms of t. All right, so this is a description of a system where we have, let's say, the blue particles. Some can be bound. There were more at the beginning that escaped. Some are already escaped at time t. And so we need to look at these two quantities. And what we are interested here, the question of interest, is what is the probability that at time 0 you enter your particle? What is the probability that you have T binding site? What is the probability? And when you look at the end of your process, so let's call it the infinity. This is the end when there are no more molecules. Of course, it's not infinity, it's a certain time. What is the probability that after your process is done, you have reached a threshold? Now it's a defective process because probably, or sometimes it can happen that if your threshold is 5, you got only 2 bonds and that's it. So what's the probability that the number of molecules equals T? And then you can ask also, when it happened, when you have this T, how long it takes. That is, you can calculate the conditional time. The time not conditioned is infinite because sometimes it doesn't happen. So you can calculate this, and you can calculate what is called the conditional time to threshold.
In particular, capital T is not a time in your first equation.
What? I'm sorry?
Capital T is not a
No,
time.
this is a threshold. This is threshold. For example, 5. 5 out of 10 or whatever, total number, let's call it S0. This is a threshold. So now we want to calculate what is the time the threshold T is achieved. Condition that the time to reach this threshold is less than the time of killing, than the time they are all, so let's say that condition that it is less than the killing time or less than infinity. I don't know how to write it correctly, but this is the idea. You want to calculate this conditional mean first passage time. Condition that this happens. So when you run simulations, you look, each time you reach the threshold, you average, so you run one simulation. You wait how long it takes to have your threshold achieved. When it happens, when it doesn't happen, you discount this realization. And this is how you do it on the computer. And now I want to calculate analytically, can we calculate this quantity, I mean the two quantities. So now for calculating this, as we have seen before, we need to write down the Markov chains. Now it's not a one, but a two-dimensional Markov chains. And now let's discuss what is the picture, the structure of these two-dimensional Markov chains, and where do we locate in this two-dimensional matrix, where do we locate this probability of having reached the threshold? Okay, so now what is this matrix? So maybe we need a big word. So now we're talking, so of course if there is an additional parameter that varies, you have to study a three-dimensional Markov chains. And you'll see already with two, it's you have to look at precisely how do you go from, let's say, time 0 where you have nothing bound to the different possibility to be bound to reach the threshold T. So let's write this. So what happens? So let's write down now the two-dimensional Markov chain. So the two-dimensional Markov chains, so for this we need to understand what happened during time t and t plus delta t. Suppose you have k bonds, molecule, k, and m particles. So what can happen? So first of all, you can, how do you come to this state? Before, you could be with k minus 1 bound, and there was m particle. So k minus 1 bound and m particle. means now you arrive to K. What does it mean? It means you bind now. Yeah, I'm sorry. Let's write it K minus. Let's write it K minus 1. Let's write it this way: K minus 1 and M. So how do you go to here? You have to bind. So now we know the rate. This is the binding rate. So this is lambda S minus K plus 1 M minus K plus 1. This is the rate. Again, we have discussed this. I'm freezing now the M, the total number of particles. I just look at the events of binding or unbinding. So this we have calculated previously. Now, what can happen also is in here, you go to K plus 1 and you freeze the number of particles. And this is the rate, K minus 1. And now we have, so this is one bound, and now you have K particles, K bound, and now you need K plus 1 bound. So what happened for this? You get additional binding, right? So this is lambda S minus K, M minus K. Now what happened? You had K particle and M plus 1. So how do you go from here to here? So there was M plus 1 particle, and now you have M, which means that you have activated your Poissonian rate, you have removed 1 out of M plus 1. Is it correct? Mm-hmm. So this is mu multiplied by M plus 1. And then finally, you have, and I think that's it, no? Because K, no, if you have K, Km minus 1, what does it mean? That is, yeah, okay, now Km minus 1, which is the rate, mu M. That is, there was M particle and 1 is living. Are we correct? I think so. Mu, no, I'm sorry. I made some mistake. Just, I'll go back 1 second. M, if I have K bound, the number of molecules that are free, because you can only kill those who are free. So if they are bound, the number that are free is M total minus K. So this is here minus K. And here this should be M minus K plus 1. Okay, so this is killing. And why don't we have here, if you're bound, okay. And here I think I am in the irreversible case. That is when you're bound, you do not get, that's right. Here when you bind, I assume K minus 1 of what we have discussed here is 0. K minus 1 is 0. It's very hard if you have K minus, we didn't know how to analyze with K minus 1. All right, so that's why here you don't just go back. We assume here K minus 1, which is the backward binding rate is 0. All right, so now let's position the matrix, and then we'll continue next week to, I want to design here to show the matrix, and then to position what we are interested in. So let's start. 0, number of bound at time 0 is 0. What is the total number of particles? M. Now you have to have, double check everything, but should not make any mistakes. So we agree, time 0, total number of bonds, 0, total number of particles, n. Now what can happen in one direction? You can have one bond and no killing. You can have two bonds and no killing. You move on until you reach T and M. And then you are finished, because this is the state where you're interested in, right? You have T bonds, and of course, there are more M than T. You know, T is lower than M. So we have now finished. If you arrive here, this is a state that we're interested in. You reach the threshold. And then now we have to continue and put on the lines what happened after you killed one, you killed two particles. So now we have 0 bound and 1 particle was killed. And now we can continue like this, n minus 1, and then we arrive to here, which is T, and then we have n minus m, and T, n minus 1. We have 1 particle was destroyed, and we reach the threshold. And then we continue up to where? We continue.
And you can have down arrows between any of those processes on the first 2 lines, right?
I'm sorry?
You can have down arrows between any
Okay, I'm sorry, I have, yes, sorry. Yes, this is very important, because now the arrows that you just mentioned, this is exactly what we have here. Yes, absolutely. So let's do the number. So we have 0 n minus 2. I'm sorry, I started to be tired. N minus 2, and now we have 1 molecule was bound, and m minus 2. M minus 2. And again, as Peter said, we have now arrows from this state and from this state. So we have now the arrows that goes in these directions. That is, they are irreversible. When the particle is dead, it cannot come back. And when you are bound, you cannot come back. So this is now an interesting diagram. Interesting in the sense that we can do something and trying now to find when and how we are going to get to this interesting stage. So now let's say this is 0, and now we need to go to m minus t. And then again, this is 1, m minus t. And then we are going to arrive here to t bound m minus t.
It's a finite difference scheme in 2 dimensions with 1-dimensional chains on the boundary.
Yeah, that's right.
Yeah.
That's right.
Yeah.
So now, am I correct? Yeah. This is exactly this, just numerical scheme. And what are we interested in? We're interested in calculating what's the probability that you end up here compared to when we arrive then. If you're not in here, you are not your probability is not. You're not interested in this. This is going to give you exactly the probability, all the cases, for the probability to have reached the threshold during your process. Now start the combinatorics. How do you arrive to one of those stages? So we say this is a starting point. To arrive to this guy, there is only one case, one possibility. Just go straight. That's it. Because if you do one, that's it. You cannot come back. So this is not very hard to calculate. The probability of being this is the probability of transition from one of these guys. Now if you start with this, now we start to see what happened, where the combinatorics is coming from. Now how you can go to this guy, you can go first this way, and then you go down. Or you can do any steps. You have to sum over all this possibility. You do one jump, and then you move this way. And then, of course, with number 3, it's going to be the same. We have an additional layer of complexity. You can go from here, do one jump somewhere, and jump somewhere. So then we have to sum over all these possibilities. All right? So next week, I think now I'm exhausted. Next week, I will write down the sum. Now we understand what we need to calculate, which is not very hard. Once we have done all of this, we need to calculate as a function of the, we'll see now the transition, the rate transition, we just calculated them. We can calculate the probability, the transition probability, for example, the probability to make a transition from here to here is going to be the rate here divided by the sum of the 2 rates. And so next week, I'm going to finish by this. We'll see how do you calculate this transition probability. How do you express this in terms of all this transition probability? And this will give us a formula for the probability of the mean first time to threshold. And then we will calculate the time, and the time is going to be the time to arrive in one of those states. And then we'll have to sum of all the possible paths. And so that's the combinatory that is behind. It's not very hard once you understand how things have to be calculated. Okay, so this is one example, and then what I'm not going to discuss what is in the paper. Suppose you have 2 types of threshold, T1 and T2, because you can bind, suppose you can split your binding sites into 2 types of binding sites, let's say red, and so you have one type of binding sites, this is the binding site in purple, and now we have another class of binding sites. And now you can ask, suppose you have a certain number of them, what is the probability that you reach the threshold for the first class before the threshold for the second class? So this I'm not going to answer. This is more or less the same, and now you have to split in between 2 type of, basically here, you have to split. And then you can ask, what is the probability you reach this before you reach this? But again, this is motivated by some biological applications. So you can have many variants of all of this. What I never worked on, and I wanted to do that at some point, and we don't have results, and I think maybe this is possibly a PhD, it's to look at what happened when the number of molecules here can vary in time. That is, you have some, let's say, fluctuations or changes in the number of molecules, total number of molecules. Let's say, for example, with the sinusoidal waves, sinusoidal functions. Okay, so I'll stop here. Next week, we will write the matrix. I mean, we have written the matrix, I will write it. And I'll finish and write the formula. And I think that's it. I think this is the basic ideas of how we calculate asymptotic expressions using Markov chains, using boundary conditions in Markov chains. Next week, I wanted to discuss actually the paper with Kevin, how we did it for this messenger RNA. We could calculate some up to a certain point because this was more involved. And at some point, we used computer simulations, but so we could still predict the behavior, which was interesting, how it depends on this bad guy versus the good guys. All right, let's stop here.